This video series is meant for Regents Geometry students, particularly in New York State Public Schools, who want a little extra review on particular topics. This one will be about the thinking and approach to composite volumes. That's these complex three-dimensional shapes made up of simpler ones, and usually the problems will involve calculating the volume of each individually and maybe doing something with the density of some material that's contained in them. The best way to use this video as a study resource is to pause it at the start of each problem and make a fair attempt on your own at solving it. Then you can unpause and follow one guy's approach, that'd be me, to see if you've arrived at the correct answer. Let's get right into it. Here's our first problem. A fabricator is hired to make a 27-foot long solid metal railing for the stairs to the local library. This railing is modeled by the diagram below. The railing is 2.5 inches high and 2.5 inches wide and is comprised of a rectangular prism and half cylinder. The question, how much metal to the nearest cubic inch will the railing contain? It is asking you to calculate the volume. You can tell because it's asking for a measurement to the nearest cubic inches. We measure volumes in cubic units. The most important thing here is not the text but the diagram. We can practically ignore the entire body of text and just calculate the volume of this shape, which is made up, admittedly, as the question did tell us, of a rectangular prism, which I'll highlight here in blue, as well as a half cylinder, which I will highlight here in red. Alright, nice. Hopefully, as you're studying this diagram, you'll notice the nasty trick they've attempted to pull on us, giving a dimension in feet where the other two are in inches, and asking for an answer in cubic inches. This 27 feet will not be allowed. We'll have to convert it to inches before we do absolutely anything. And we can do that by setting up a proportion. Let's say that there are X inches in 27 feet, like there are 12 inches in 1 foot. A quick and easy cross multiplication and you can conclude that x is equal to 324 inches, which we will replace with the 27 feet that's there and use in our volume calculations. Now this is of course a composite volume problem, and we're going to calculate the volume of the whole shape by calculating the volume of the simpler shapes individually and adding them together. We're going to start with the rectangular cylinder. Our reference table says that, did I just say rectangular cylinder? I meant to say rectangular prism. Anyway, our rectangular prism in blue, our reference table tells us that the formula for a general prism is base times height. What they mean by base is any surface you choose as being the bottom of this thing, i.e. in this case a rectangle, and the area thereof. So when they say capital B for base, we're thinking length times width, and then times the height. Length times width times height is how most of us remember the volume of rectangular prisms anyway. And we're going to plug in, for the length, we could use our 324 inches. And for the width, we can use our 2.5 inches. Now for the height, looks like they're going to throw another trick at us. Look at how this 2.5 inches looks like the height, but actually that goes from this to this side of the shape. It's not just the height of the prism, but actually the height of the entire shape. Now I'm going to make an argument here that this red circle, hypothetically, fits within this 2.5 by 2.5 square. So the argument I can make is that the radius of that circle, we'll need that later, but more importantly for now, the height of our rectangle is half of that diameter. Okay, half of that 2.5, which is going to be 1.25 inches. I'll keep that, I'm going to need it later. So I'm going to plug in 1.25 for my height, and then I'm going to run these numbers in my calculator to get the volume of the rectangular prism. And that's going to come out to be 1012.5, 1012.5 inches cubed. Now let's move on to the volume of our cylinder, actually in our case a half cylinder. So when I write down the formula for this, we're going to slap a big 1/2 on it and follow it up with the general formula for a cylinder as given in the reference table. 1/2 pi r squared h. Plugging in, for our radius, we're going to have to use half of this circle, which, remember, we kind of figured out to be 1.25 inches. So we'll plug that in, and for the height, which we'll say is going this way, we're going to use our 324. This quantity, give me a second while I calculate it. It's 1.25. I'm just plugging into my calculator here. And we got 795. 795 point, let's say, 216 inches cubed. Alright, great. So now we're getting down to the end here. We're going to need to add these two volumes together. And when we do that, we're going to wind up with 1807.716 inches cubed, which is awfully close to 1808, and the answer is 3. 1808 inches cubed. Okay, here's our next one. A vendor is using an 8-foot by 8-foot tent for a craft fair. The legs of the tent are 9 feet tall, and the top forms a square pyramid with a height of 3 feet. Now, what is the volume in cubic feet of the space the tent occupies? Well, at least they're not being super mean, and they're giving us everything in feet. That certainly makes things a lot easier than it was in the previous problem. Once again, we've got two shapes to consider here. I've pretty much got a nearly cube-like shape, but technically it's a rectangular prism, because not all 3 dimensions are equal. 2 are 8 and 1 is 9, so I'll mark that in blue. But I've also got a new shape here, the square-based pyramid, which this time I will mark off in red. There's a square base, and it kind of comes to a point. To calculate the volume, we'll look at each shape separately. We'll look at the volume of the rectangular prism, which once again, just like last time, we'll use length times width times height, whereas they choose capital BH over here on the reference table. That B is referring to this square in this case, which of course the area of that base is 8 by 8. Length times width will be fine to represent that. We'll use 8 times 8, and for a height, we will use 9. Okay, really way simpler. 8 times 8 times 9 is going to be 576 cubic feet. Now we're going to look at our red pyramid, and that one is given here. So the volume of the pyramid, once again, they're going to give us 1/3 capital B H, and that is referring to the base, the area of the base, which is the same square as the area of the, or actually has the same area, of course, the same dimensions as the base taken up by the rectangular prism. And we have to actually use length times width. In this case, the same length times width. And we're going to plug in 8 for length, and 8 for width, and 3 for the height. And we're going to wind up with a volume for that pyramid of 64 on the nose, 64 feet cubed. So we will add 576 and 64 and get 640 cubic feet on the dot. I like that one. Okay, now here's a good one. A solid metal prism has a rectangular base with sides of 4 inches and 6 inches and a height of 4 inches. A hole in the shape of a cylinder with a radius of 1 inch is drilled through the entire length of the rectangular prism, and they want to know the approximate volume of the remaining solid in cubic inches. So once again, quick check, all the dimensions are the same. That is the least they could do for us. Now we want to be careful and get a really good sense for this. Watch this. This is a two-dimensional view of this side, but really this cylinder here has been drilled all the way through. So I'm going to try and complete the picture just like they described it. They described a hole being drilled through here with a radius of 1 inch. Now that shape is negative space, okay? We're going to subtract the volume of that cylinder from what would otherwise be a complete rectangular prism. We'll use black to represent the rectangular prism and green to represent the negative cylinder space. And once again, we'll calculate the volume separately, and this time we're going to subtract, okay? So the volume of the rectangular prism, just like before, will be length times width times height. Pretend it's all there and there's no hole. We will use 4 for a length, and 4 for a width, and 6 for a height. Not that it really matters which of those goes which. Alright, and this quantity is going to be 96 cubic inches. Now we're going to jump to that negative space and talk about the volume of that green blank cylinder. And the volume of a cylinder is still what it was. It's going to be pi r squared h, not a half cylinder or anything wacky like that. Full cylinder. And they gave us the radius pretty clearly. Sorry for kind of covering it up here, but they did tell us that it was 1 inch. So pi 1 squared, and the height of this cylinder goes that way, along the same line as the 6 in the rectangular prism. So we're going to plug in 6 there as well, and that's going to be 6 pi, or when you approximate that with the calculator, 18.849, let's say. Actually 18.850 if I round correctly. Alright, this time we're going to be after the subtraction of these two. We'll do 96 minus 18.85 and get 77.15 inches cubed. That's pretty close, and close enough, of course, to option 2. Okay. A company is creating an object from a wooden cube with an edge length of 8.5 centimeters. A right circular cone with a diameter of 8 centimeters and an altitude of 8 centimeters will be cut out of the cube. And now which expression represents the volume of the remaining wood? This is not an easy picture to draw, okay? I'll make an attempt at it in a second, but actually I think the best way to solve this problem is to employ what we employed before, which was basically the volume of a cube minus the volume of a cone, or in the previous problem it was a cylinder, but in this case we're obviously subtracting a cone. And we just need to plug in the appropriate formulas. We know that the volume of a cube will be, well, it's a rectangular prism, so length times width times height works, but actually all the length and the width and the height are the same quantity. We could call it length times length, or length cube. And we can put in the volume of a cone straight from the table as 1/3 pi r squared h. Now, specifically, we know that the length of the cube is 8.5, and we have our 1/3 pi, and we were told that the radius, well, actually we were told the diameter of the cone as being 8, so the radius is going to have to be half of that, coming in as 4, and an altitude, which is a fancy word for height, of course, we'll put in as 8. We don't even need to plug this into a calculator or anything, because this is the format of the answers. Let's see which one matches. I think, yeah, it's number 4. Matches perfectly. Number 5. A storage tank is in the shape of a cylinder with a hemisphere on the top. The highest point on the inside of the storage tank is 13 meters above the floor of the storage tank, and the diameter inside the cylinder is 8 meters. Determine and state to the nearest cubic meter the total volume inside the storage tank. So here maybe you could guess that what we're dealing with is a cylinder, which I'll demarcate here in blue. And on top, we have a hemisphere. That's a half sphere. And as usual, the problem to calculate the volume here will be to pick out the relevant dimensions and just add the blue volume to the red volume. What I'm going to attempt to do in advance of everything is try and simplify the diagram. If I'm going to be after the height of a cylinder, which I will eventually, because of the formula for a cylinder, which calls for pi r squared h, then I can't use this 13. What I'm going to have to use instead is a certain number that goes here. What can we get from the text here? Well, we know that the diameter of the circle that is actually the intersection of both the hemisphere and the cylinder is 8. Okay, that means that the radius of the hemisphere is 4. This is 4. This is 4. Now that 4 is included in this 13, so we're going to chop off that 4 to represent the height from the ground to the top of the cylinder part, and that's going to give us 9 meters for that. So that's enough information to get the volume of the cylinder. Let's plug in to our formula pi r squared h. That's pi. Well, the radius of the cylinder is also the radius of the hemisphere. Pi 4 squared times 9. So this expression is going to evaluate to what I'll call 452.389 meters cubed. Now we'll move on to the red hemisphere. So the volume of the hemisphere is generally going to be the volume of a sphere, given here by this formula, but of course we've only got a hemisphere. Half of it, we're going to slap a big old 1/2 onto what would otherwise be 4/3 pi r cubed. Only one thing to substitute there, the radius of it, which we already know to be 4. And in so many steps, this is going to evaluate to, one second, about 134.041 meters cubed. And as usual, I'll be adding this and that, which in my calculator is going to give me 586.43 or so, but then again, they did say state to the nearest cubic meter, so we're just going to knock off the 43, round down to 586 meters cubed for the total volume of our tank. Now to finish this video with this monster of a problem. Here we have a rectangular in-ground pool being modeled by this very multifaceted prism. The inside of the pool is 16 feet wide. Okay, so all of this text here is going to be describing what the diagram can tell us quite succinctly. I will not read it. But what we do need to know starts here. If the sloped floor has an angle of depression of 16.5 degrees, as indicated, what is the depth of the pool at the deep end to the nearest 1/10 of a foot? Alright, the depth of the pool at the deep end is going to be this dimension right here. That is what I would like to know. And we know it's at least 4.5 because it sort of drops off from the shallow end, which is definitely 4.5, but then there's this part of it, which is unknown, and we need to add to that 4.5 to express the deep end of the pool. We're going to need to use some trigonometry on that triangle there. Okay, so this is where I'm going to call up my SOHCAHTOA skills, but not before assigning the relevant dimensions to this triangle. If you look at this real quick, you can see that the long dimension here is 35. This side is 12.5. This side is 9. And if I take 35 and subtract 12.5 and 9, I get a dimension of 13.5 for this side of the triangle. And I'm going to employ my SOHCAHTOA here, our good friend, to try and state something trigonometric that is true. I'd be interested in this side, which I'll call x, and note that relative to the angle, I have sides of interest opposite and adjacent. So I'm going to call up tangent. We say the tangent of an angle theta is the opposite over the adjacent. Specifically, in our case, we have that the tangent of 16.5 is equal to x over 13.5. We will do the cross multiplication, which will suggest that x is equal to 13.5 times whatever the tangent of 16.5 is. That quantity, and do make sure that your calculator is in degree mode for this, that quantity, 13.5 tangent 16.5, does turn out to be just about exactly 4. Calculator is trying to tell me 3.9988. It wants to be 4. So x here equals 4, and thus the deep end is going to be 4 plus the 4.5 on the shallow end. So we know that to be 9.5. That answers the question there. So I guess I'll write here that the deep end is 9.5 feet. Now let's try and tackle the real beast of this problem. I guess not, it's not that big a deal. Find the volume of the inside of the pool, the whole thing. Alright? Now, I know someone spilled some trigonometry in our volume problem, but hopefully by now you know that the basics for solving volume problems involves identifying all the composite shapes. So in blue here, I'm identifying what I pretty much can see as one big rectangular prism. Pretty tough to draw a straight line on this thing. Alright, that should be good enough. In green, I have a new shape for today, a triangular prism. Alright, that's very nice. And finally, I have a much smaller rectangular prism on this end. And we should have most of the relevant dimensions on the screen already. We will have to deal with the volume of the blue rectangular prism, length times width times height. That's going to come in at, let's say, 35 times a width of 16 and a height of 4.5. So 35 times 16 times 4.5, 2520. Let me do the green one last. I have a red rectangular prism. We'll run length times width times height. This one has a length of, let's say, 12.25, at least going the same direction as that length. A width of 16, let's say. And a height we've identified of 4. That one's going to be 12.25 times 16 times 4, so 784. Okay, finally the new shape, the volume of our triangular prism. Okay, the table here has a general prism, not a triangular prism, but a general prism down as capital BH. You'll remember B represents the area of a side, okay, an area of a base, if you will. And anything can really be the base, but it makes the most sense to make the triangular prism have a base of a right triangle here. The area of a right triangle is 1/2 length times width and times height. Right, so that there is the capital B part. And we have a length of what could be 13.5, a width of what could be 4. You could say height, but then you'd confuse it with the actual three-dimensional height going this way, which is definitely 16. And 1/2 times 13.5 times 4 times 16, and we're in at 432 feet cubed. Alright, and we're going to add these quantities together and find that our final answer for the volume of this thing to the nearest cubic foot is actually 3,736 feet cubed. There is more to this problem actually, but I have cut it from this video because it ceases to be a volume problem and actually begins to be a density and time calculation problem. So I'm going to cover the rest of this problem in another video. Hopefully this was helpful just from the volume perspective of how to deal with composite shapes. Good luck on the Regents, good luck on your exams, and let me know if this video was helpful for you.